All right, so today we're going to continue working with finding limits, and we're going to be looking at some more with algebraically. It's just going to look a little different. We're going to add some more skills in there, different types of problems. So there are some limit laws. The limit of a sum ends up being the sum of its limits. And then the limit of a constant multiple, how you get that is the limit of a constant times a function is a constant times the limit of the function. So some examples are down here. We've got the limit of f of x plus 5 times g of x there. And notice this time that x there approaches negative 2. So what we're going to do is we're going to pull these apart here. We're going to do the limit as x approaches negative 2 of f of x plus we're going to do you can take 5, you can take the constant times the limit of the function, so I can pull this apart. 5 times the limit of g of x, whoops, g of x, and this one over here as x approaches negative 2 as well. So we're going to go ahead now. So I pulled that all apart using the two rules that are up there. You've got the sum of them, and then you've got the constant goes times the limit of g of x there. So let's go ahead and let's find this value, and then let's find this value, and then let's multiply it times 5 there, and then add them together at the end. So the limit of f of x there as x approaches negative 2. So looking at our graph here, our graph looks like this right here. So I'm going to go over here and I'm going to find negative 2. So finding negative 2 here is right here. This is where my negative 2 is. So I'm looking at the graph there. Remember, I got to go from the left. And it seems like your limit there is approaching 1. And if I go from the right, my limit is also approaching 1. So the limit as f of x as x approaches negative 2 there is 1. And now I'm going to come over here. I'm going to do the limit as g of x there, the limit of g of x there as x approaches negative 2. So the g of x function, I don't know if you notice down here, but this is your g function right here. And this is your g function over here as well, the lines. So the curvy part there is your f, and then your straight lines there is your g function. So coming down here, we're going to look at negative 2 as well. So we're looking at right there. So from the left there, it approaches negative 2, and from the right there, it approaches negative 1, because that's your negative 1 is down here. So approaching negative 1 in each case. So I'm putting negative 1 in there. So now I can just do my math. 1 plus a negative 5 gives us a negative 4. So our value there ends up being a negative 4. So we can go ahead and pull apart your sums and take the constant out of something where you got the limit of 5 times some kind of a function. So now we've got the limit of a difference. So that ends up being the difference of the limits. So here you've got the limit of f of x minus g of x as x approaches 1. We can just pull them apart. So I'm going to do this portion, find that one, minus, I've got the limit of g of x as x approaches 1. So now I can find it says the limit as limit of f of x as x approaches 1, there's 3. And it says the limit of g of x as x approaches 1 is negative 2. So plugging those in there, I get 3 minus a negative 2 there, gives us a limit there of 5. So when you subtract, we just take the limit of the two functions being subtracted there, we get 5. So again, the difference of the limits. The limit of a product is the product of the limits. So you can find, again, you can pull them apart. I can go the limit of f of x as x approaches 1, and I can multiply that by the limit of g of x as x approaches 1. So now again, I'm going to recognize where my g function here is. There's my g functions. And then the red portion here is going to be the f function. All right. So now looking at that, we can see that as x approaches 1 there, so I'm going to also draw in here a little bit so we can actually see the axes a little bit better. So we've got as x approaches 1, and we're looking at the f function here, so that's right here. So you can kind of look here from the left there, we're approaching 2, and from the right there, we're approaching a limit of 2. And then the limit of g of x as x approaches 1, so approaching 1 here from the left, your value there approaches negative 2, and approaching here from the right here, it's approaching there at negative 1. Notice they're not matching. Since they're not matching there, we're going to go ahead and say it does not exist. Remember, I like to abbreviate does not exist with DNE. So can't do that one. Limit of a quotient. That's the quotient of the limits provided that the limit of the denominator is not 0, because remember you cannot divide by 0. So to do this one, we'd pull this apart and we'd say the limit of f of x as x approaches 2 divided by the limit of g of x as x approaches 2. So again, using the same graph that we had over here all along, I'm going to quickly do the green portion and the red portion, darkening my axes one more time. All right, so now let's look at this one. So the limit of f(x) as x approaches 2. So now we're up here at 2, so there and there. So it's looking like that value right there, which is looking like 1.5 to me, or 3/2. And then if I look there at g of x as x approaches 2, so from the left here, we're approaching there, and from the right, we're approaching there as well, so that value there is 0. So you've got 1.5 divided by 0, so you can't divide by 0. So undefined does not exist. So coming over here, there are some special limits here. You've got the limit as x approaches a of c there is equal to c. So you can kind of just think about that if you just got a constant. So if I got 5 there, and limit as x approaches 1, of course, you know, it kind of like be a graph here, and you'd end up with a horizontal line up here at 5. And because they're up there at 5 there, as it approaches 1, so as you get 1 would be here, let's say 1's here, so you approach from the left, you approach from the right there, and you're up there at 5, so your limit there would be 5. And then the limit as of x there, as x approaches a there, so if you just think of a value there, so for instance there, let's say you got x approaching 1 there. So we can just go ahead and just substitute 1 in there, for instance. So I can just do the limit as x approaches 1. Since x is approaching 1, I can substitute a 1 in there for x. Well, of course, the limit of 1 is just 1. Again, kind of going back to your rule number 1 there. And then number 3 there, you can kind of look at that one. The limit of x to the nth as x approaches a. So let's just, for instance, put a value in there of 2 for a. So as x approaches 2, we say it's, I see, this is supposed to be some power, so I'm just going to put a 3 down there. So we can go ahead now and just go 2 to the third. So we end up getting the limit as x approaches 2, we end up getting 8. So we end up getting a limit there of 8. Same thing with this one down here, the limit, and let's say x here, something different. X approaches 8 there. Let's do the cube root there again of x. And we can substitute our 8 in there. So the limit as x approaches 8, let's substitute 8 in there for the x. Take the cube root of that, and we get 2. So you can use direct substitution to be able to solve something like this. And if those aren't making sense to you, it will as we go through the next few problems here. Evaluate the following here. One way to evaluate limits when you're given a problem like this is to go ahead and just use direct substitution. So just go ahead and substitute 5 in for your x's. And get your value that way. So our value after plugging into the calculator there ends up being 39 because we get 50 minus 15 plus 4 there gives us 39. Same thing with part B, you can just use direct substitution. The limit as x approaches -2, provided that you don't end up getting a 0 down your denominator. So doing that, we could end up getting the limit, well, yeah, as x approaches -2 there, then ends up being, what do we got, -8 minus 4 minus 1 all over 11. Oops. This should have been a positive 4, so this should have been a positive 8. There we go. So we end up getting -1/11. So there's our limit for that one. So again, we can use direct substitution just like I showed you. So the limit of f of x as x approaches a there is equal to f of a. So we can go ahead as, again, we cannot get a 0 down in our denominator when you use direct substitution. If that's happening, we're going to have to use some other method there. So part C there, let's go ahead and let's evaluate this. So the limit as x approaches 3, 2 times 3 to the third minus 10 times 3 minus 8. So we end up getting 16. And then down here, we can do the limit as x approaches -1. -1 squared plus 5 times -1 all over -1 to the 4th plus 2. So what do you get? 1 minus 5 there is -4 all over 1 plus 3 is, or 1 plus 2 there is 3. Yeah, -4/3. So there's our two limits just using direct substitution. So direct substitution is one way of being able to do this. Some other ways of being able to find limits is by canceling a common factor. So you have to remember how to factor. So if you remember, the bottom here is the difference of squares. So I can go x, one's a plus, one's a -1. The x minus 1s there cancel out. So I end up getting a limit as x approaches 1 of 1 over x plus 1. Now I'm going to substitute 1 in there. So I really end up getting, what is that, 1/2? Canceling out a common factor is another way of being able to do that. You got to realize that the difference of squares, x plus 1, x minus 1. You can cancel out the x minus 1s. You get 1 over x plus 1. Substitute the 1 in for x, and you end up getting 1/2.